Now this is 15.89 into 1.2, that is your minus 19.068 kilonewton. Why I have used minus is to show the direction of its action. It is away from the structure, that is why minus. It is towards the structure, that is why plus. So if I sum it up, this 6.432, it's having its components, that is WDLZ and WDLY, whereas WDLZ is nothing but WZ, whereas in case of Y it is going to be, we have seen here in the previous uh, slide, WWL plus WDL cos theta. So WWL is minus 19.068 plus WDL cos theta is plus 5.75, which is equal to minus 13.32. So the net effect is going to be negative, which is minus 13.32. Similarly, you have to calculate for this. Now, after calculating, these are the forces acting on it. Now, you're going to calculate the moment and shear force, because the purlin is a simply supported beam member. So, this we are going to calculate it. Why we are not considering as an UDL instead of concentrated load is, concentrated load will give a maximum effect of bending moment and shear force compared to your UDL. That is why we are considering the maximum effect. So you are due to concentrated load along Z and Y direction, we are calculating it. Here if you see, you have to see it clearly. This WZ is acting in the horizontal direction. So WZ will create a bending in Y axis. So your My will be equal to WL by 10. Therefore, Wz into L by 10, because Wz is a horizontal force which is going to create a minor axis moment. Similarly, the vertical force is Wy. So Wy will create a major axis moment Mz. Therefore, Wy into L by 10 is equal to Mz. But the force along the same direction is going to create the shear force. Therefore, concentrated load is W by 2. Therefore, Vz, shear along Z direction is your Wz by 2, horizontal shear, and shear along Y direction is your Wy by 2, that is vertical shear. So you have to calculate based on this various combinations. We know what is Wz and Wy from the previous one. So you are going to take these values of these combinations and consolidate it over here. So you write it down with the sign values, because this shows it is away from the structure. Next, you have to calculate what is Mz, My, Vz and Vy. Out of these four values, which one is going to create the maximum effect? We are going to take that forces and design it, but appropriately. We should not take the value of Mz here and the maximum. For example, here Mz is 8.16, maximum of My is 1.44, and Vz, if you see, maximum is 1.8. So you should not take it like this. Instead, you have to take it in such a way that if you are taking Mz, the corresponding My and corresponding Vz and corresponding Vy you have to consider. So after taking all these values, we are going to write it down, which is the worst combination and what are the forces acting on the purlin. So this is for this combination only, this is the forces. Now you have to design the purlin as a beam member. So as usual, what we will do is, we will calculate the Z required. So Z required is equal to M by Fy into 1.4. If you multiply, you will get what is Z required. And based on the span for deflection criteria, we know the maximum force is along Y direction, that is Wy, but this is a factored loading. You might have seen here. This is for, this 20.4 is for 1.5 factored loading. So you have to divide it by 1.5, and this is your concentrated load, because for deflection you have to use unfactored loading. So for unfactored loading, this is 13.6 kilonewton. Concentrated load, the deflection formula is WLQ by 48 EI. E value, Young's modulus of elasticity is 2 into 10 power 5. You don't know the value of I required, because that is the one we are going to calculate. So equating it is your del allowable. What is your allowable deflection? For allowable deflection, if you refer IS 800-2007 table number 6, there is a value for purlins and girts, where for wind load or live load, And there are two values which is given over here. One is for elastic cladding, another one is for brittle cladding. The problem statement itself tells you that it is a GI sheeting. Therefore, for GI sheet, it is an elastic cladding. So for that, for purlins, the allowable deflection is spanned by 150. So what is the span of the purlin? It is 4 meters. So 4000 divided by 150, this is your allowable deflection. When you equate with allowable deflection, you will get what is the I required, that is the inertia, moment of inertia required along its major axis. Because major axis is the one, the maximum loading axis. Now, based on your modulus required and your inertia required values, you choose a cross section from SP6 for a channel section. For I have chosen for which satisfies the two criteria is ISMC 125. I took down the values from the code and I have written it over here. And now I'll do the sectional classification. Why we are doing sectional classification is to check whether the member is safe against local buckling. So BYTF, I'll check it out. It is less than 9.5. Here, if you see for channel, B is your entire flange width. For I section, it is flange width divided by 2. So this figure in near table 2 itself, it is shown here. So you can refer the figure next to your table 2 in IS 800-2007. So it is a plastic classification. For D by TW of web of channel, you have to deduct the flange thicknesses and check it out. It is 42 epsilon. It is again plastic. So your beta B value is 1. Now check for shear. Design shear force is equal to AV into Fy by root 3 gamma m naught. You know what is your depth of the section. For rolled section, the entire depth is your shear area. So 125 into thickness of web into 250 is your yield stress of the steel divided by root 3 into gamma naught m naught, which we will take it from table number 5 of IS 800-2007. So 1.1. So you know what is VD value. You check against 0.6 times of VD, which is greater than your V actual, that is maximum of your VZ and VY. Your VY value, you know what is your VY value here, that is 10.2. So maximum of VZ and VY is 10.2, whereas your 0.6 VD is higher than your V actual. Therefore, it is safe against shear. Now we are going to check for bending, but the purlin is experiencing bending both in major as well as in minor axis. So you have to check bending against major as well as minor axis, and then finally check for combined interaction. So MdZ is equal to beta B ZpZ Fy by gamma m naught, which should be less than or equal to 1.2 ZtX Fy by gamma m naught, which is nothing but your major axis. So if you check it out, the values out of this two value, if you see this value is less than 1, so I am taking this value 17.53. Whereas the moment acting on the purlin is 8.16, so it is safe against bending along z-axis. For y-axis, I have to check it out. For y-axis, I need to know two section modulus, that is your elastic section modulus, another one is plastic section modulus. For this plastic section modulus, you will take it from IS 800-2007 annexures, but for us y-axis plastic section modulus, you have to calculate. So its value is not given in the code book, so we have to calculate. So x distance plastic neutral axis you have to find out. This is nothing but the axis which separates the cross section in equal areas. So assuming x, and I am calculating the equal areas and finding out what is x distance, and next I am finding out above and below the axis area into y is my ZPY. I am calculating it. If you go through, you will be able to understand. It is clearly written over here. Now finally I found out what is ZPY. After finding out ZPY, I am calculating these two values. Out of this value, in case of minor axis, if you see, this value should be less than or equal to this value, right? That is based on the equation. If you see, this value should be less than or equal to this value. But after calculating plastic modulus along minor axis, I found out that this 8.466 is higher than 3.573. So out of these two values, based on codal provisions, this should be the maximum value. So 3.57 is the major